Hello, this is part 3 of a talk on evolutionary epistemology in Silico. I'm talking about how neural networks can teach us interesting things about nature and nurture. So we are on our way towards a universal grammar in a large language model. I reviewed in the first portion of the talk how Chomsky has a very negative view of our ability to learn about language acquisition from LLMs, but I noted he was thinking of them only in a kind of empiricist mindset, which aligns with the way they are typically trained. In the previous portion, I talked about evolutionary meta-learning, which is a different way of training neural networks, which will allow them to develop over an evolutionary scale innate structures, such as, I'm now going to argue, a universal grammar. So let's first estimate the amount of data that went into forming our innate language faculty, assuming that we have one. If we think of a parent-to-child baton pass of linguistic experience, 100,000 years of behavioral modernity times 20,000 words per day comes to 730 billion words, which equates to about 1 trillion tokens. Now, interestingly, GPT-3's training scale was in about 300 billion tokens, and now training runs are currently in the trillions of tokens. So we have this evolutionary scale of data being put into these large language models to get them up to linguistic competence. So whereas engineers have applied this evolutionary scale of data to a single training run, if we were to instead use these evolutionary meta-learning techniques, which I just highlighted, linguists could be able to evolve an initial state in an LLM with this level of evolutionary data, right? So by leveraging kind of bitter lesson scales of data across many outer loops, the idea is that you can get to poverty of stimulus levels of data efficiency within the inner loop. At least that's my hope. And I'm working on this with a student. It's early days though. But as a proof of concept that this process would work and that it sort of deserves the compute we're about to throw at it, consider a simplified example where we have a single language, so not multilinguistic, but just one language, and I'm going to produce variants of it by scrambling the token list. So this next portion of the talk requires a little bit of knowledge about how large language models work, but I'll explain what's needed as we go. So think of English and think of some permutation G of its token list. Tokens are roughly to the LLM what morphemes are to us, so the smallest bits of semantic meaning. They don't quite line up with our morpheme list for technical reasons, but there is a list of semantically meaningful tokens for the network. And suppose that things like S and LY, these are morphemes for us that mark pluralization and convert adjectives into adverbs. These are little semantic functions which are reliably played by a certain unit of the language. LLMs have a kind of similar thing in their token list. But consider English, but with a swap. Swap these two semantic functions so that we now pluralize with ly and we mark adjectives transforming to adverbs with s. So this would be a permutation which just swapped these two semantic roles, but in principle you could imagine versions of English where you swap around all of the semantic roles, and technically we're meaning that with the permutation of the token list to make it concrete. Now, the signifier-signified relationship is mostly arbitrary, so that English and all of its permutation, G-English, is a different English, are all possible languages from a kind of evolutionary perspective. Evolution could have produced any one of them. So they're all going to count as possible and should be equally included in our kind of evolutionary history. So any language task that you might have for English, if you wanted to do next token prediction, which is what the LLMs are trained to do, there is a corresponding task for G English. Okay, so I have a symmetry that acts on the language, on the token list, and also on the tasks. I've got a symmetry acting in all of these spaces. Now, if you gave me a well-trained network on English, some theta n after a lot of training you might get there, I can, and literally I mean this, I personally can go in and manually alter the parameters so that it becomes a network that is well trained on G English, right? So how do I do that? This G transformation, I want to enact it on the weights and biases to get a high performance network in the modified language. Well, all you did was switch the token list. So all I have to do is undo that at the next available step. So LLMs, the way they work, they take the tokens, there's an embedding step where they turn them into vectors, and then they do a bunch of vectorial semantics on them. And then at the end, you take a vector output and you convert it back via a de-embedding process into a token. So if I take the embedding and de-embedding steps at the very start and the very end of the process, if I permute which vectors they get assigned to in the same way that you permuted the token list, I can just undo the permutation that you did. So really, I get an equal performance network on the new language, G English, by doing this kind of transformation. Okay, now we have set up the tasks. These are the various tasks that we're going to meta learn on, which again, from the previous section, has an evolutionary interpretation. But let's think of a lineage of large language models where each generation has to learn a different G English. So every generation learns what syllables mean and what morphemes have which semantic roles in its particular language, but then the children modify language so much that it just basically scrambles it. And every generation has to completely relearn which bits of language are using which semantic roles. That's their task in life, is to learn that. And there's no way, of course, for the baby network to know its generation's language in advance. So as before, as motivated in the previous section, we're going to take each failed token prediction to give a chance epsilon of instant death. This is giving us a kind of fitness pressure towards rapid language acquisition so that you're at least predicting the tokens correctly, so that you can follow social situations. That's like important linguistic work that our minds are doing. Now, recall from the previous portion of the talk that the change in the initialization from one generation to the next by strictly Darwinian mechanisms, and again, it's a formal equivalence that describes this process, is broken into two parts. There's one kind of reptile update, which just cares about proximity. It just tries to move the initialization towards the final train state. And then there's also a canalization term, which is more complicated. But let's turn that off. Let's turn off the canalization for now. We'll think a bit, and then I'll turn it back on in a moment. So the proximity effects, as we saw in the earlier portion of the talk, attract the state to the centroid of all the well-trained states. If you always take a move towards theta n for all of the different tasks, which we all know where they are now, for this G English example, they're all symmetrically located via some symmetry transformation we have control over. You can compute then what the center of these well-trained states are. And the evolutionary process with the canalization turned off will naturally lead to that center. What is that center? All of the mid layers of the network are exactly preserved. All I did was change the permutation in the embedding and de-embedding layers, which are just the first and last things that the network does. All that gets wiped out by this averaging, but everything else stays intact. So this Darwinian evolution, although keep in mind we turned off the canalization, if we do this evolutionary process on these LLMs and keep doing these reptile updates, it will move the LLM's initialization to have a tremendous amount of linguistic and grammatical structure inside of it. Everything that's written inside the LLM's mid layers. So the network is in this way born with a tremendous amount of innate knowledge about, say, pluralization and adjectives and adverbs. As I motivated before, these are semantic roles being played by some token or other in the language. What token, in fact, plays that role changes from generation to generation, but we still basically know about them, everything that's in the middle layer there. We just don't know what is playing that role. So this kind of deep structural information, just about English in this case, because we only have English and its variants now, but we'll include more languages in a moment. Deep linguistic knowledge encoded into theta zero, right? But as I said, the network will not know which tokens are playing which semantic roles, although in a way it knows that those semantic roles are there, and it's sort of, in a way, expecting for them to be filled, in the same way that a baby duckling is sort of expecting a mother to imprint on. It has these sort of pre-concepts ready to go, ready to spring out and latch on to something, to sort of like it's expected in that way. So each network has to only learn the superficial knobs and dials of its generation's language. It already has the principles of the language in a way, and just has to learn the parameters about how it's set by its particular language community. And this task of learning from this innate structured state should be a much easier task than learning English from scratch, right? From a random initialization. And that's, of course, exactly what it was evolved to do. We had a fitness pressure pushing us towards rapid language acquisition, and we've just seen that evolution will, and again, we turned off the canalization, but it'll build in a lot of innate structure into the initialization just to do that task. So this is the function, this is the telos, if you will, of the innate language faculty that we've been building. This is exactly what you expect from a kind of Chomskyan language acquisition device. In broad terms, structurally, it's very similar, and with a similar evolutionary origin for it as well. But let's think back to how important canalization was for Chomsky's theory. You can find that in the previous section. Let's turn on the canalization term. Let's just turn it back on. What's going to happen? Well, think about the diagrams we saw earlier. So there's one term, this reptile term, that pulls us into the center of these well-trained states. But there's another term, the canalization, which says maybe that's not the best place to start. It would be better to start up on top of a hill that has nice guided, shepherded paths that lead down to the initialization. That's what the second term here is doing. So the network will be pulled away from that centroid. We won't start at the average of all the G Englishes. We'll be pulled somewhere up on a hilltop that has a nice path down to all of them. This will only strictly improve the language acquisition process. But what does that look like? Here, you might imagine we have English and German and Japanese, although strictly now we're just speaking about different G Englishes, but you can imagine this extended to other languages as well. What's intermediate to all of those languages, there's no reason that that's good terrain to be starting out at. So I've drawn this little X here. It might be better to start over here at theta 0 and train down these canals, these developmental pathways into these languages, which would just include English, German, and Japanese because they're in our evolutionary history, and not things like Klingon or that impossible language that I described in part 1. And I'll describe it again soon, I guess. But the proximity and canalization effects, what I'm saying on this slide is that if you trained up an LLM in this way, it would answer all of the complaints that Chomsky had that we discussed in the first portion of the talk. So the first one was the poverty of stimulus complaint, that the proximity and canalization effects here will allow the large language model to learn language much more efficiently than before. It might have taken 300 billion tokens to learn a language before, as the ChatGPT 3 scale. Hopefully you can get that down to 100 million tokens, something much more like us, as referenced by the baby LM challenge. That was one of Chomsky's complaints. The other one was that LLMs in their typical training start off tabula rasa, empiricist. This is not true here. Again, we have a very rich grammatical initial state, which contains lots of important linguistic and grammatical and syntactic and information about the language. And it has to, that initial state evolved due to a kind of poverty of stimulus constraint, which we placed on the system. Now, our evolved large language model is not a general purpose pattern matcher. It's not a stochastic parrot anymore. It wasn't before, in my opinion, but now it definitely isn't, because it has a domain-specific language acquisition device. It's not that in the LLM's lifetime, in its little last bit of the training run, in its last cycle, the last inner loop, it's not that there it witnessed patterns of association between things and this is how it learned grammar. No, it had a deep structural knowledge of grammar initially. And yes, perhaps that was built by a kind of statistical abstraction from the language environments of evolutionary history. But it's not being extracted in the individual's lifetime. Maybe evolution built it that way, but for the individual, they're starting from a rich initial state and learning everything from there. And in particular, these canals and proximity effects only guarantee that we will be able to learn languages which are structurally similar to those that we've experienced in our evolutionary history. So I've placed Klingon far off to the side. Whether or not Klingon is an impossible language is an interesting question. But by impossible language, I mean more something which disrespects the hierarchical structure of language, for instance, that you form a question by swapping the second and seventh words. That's a completely non-hierarchical transformation of the sentence. And so, in fact, it's a very difficult language to learn. I discussed this more on the first portion of the talk. But the point is that these canalization effects and partly the proximity effects give us a sense of which languages are impossible. They are just those that sit away from the canalized portions of the language acquisition device, right? And in particular, you might be able to learn them eventually, so they're not completely impossible, but it might take, as we noted earlier, an evolutionary scale of data to get there, because you're not using the canals and the language acquisition device. They may be learnable in a different way, but not with the special language acquisition device that we have. Right? So I think this addresses all of Chomsky's major complaints from the false promise of GPT-3 paper. I think that LLMs, especially if you evolve them in this way, would make wonderful, valuable scientific models, and that we can, in fact, learn a lot about human language acquisition and use from them. So in conclusion, for this part of the talk, before I change topic a bit, we can leverage meta-learning techniques to efficiently and faithfully simulate the same kind of evolutionary pressures that shaped human cognition. Certain evolutionary dynamics are formally equivalent to a stochastic gradient ascent up the fitness landscape. There are implications here for teleology in biology. I haven't been able to articulate them yet. We can quantitatively distinguish between the Baldwin effect, this proximity effect, and canalization effects. I'm working with a student to quantify these things now in a toy example. It should be possible, though, to evolve a large language model with a language acquisition device given to it via a poverty of stimulus fitness constraint. And I just encourage I encourage linguists to apply this level of evolutionary data to evolve an LLM's initial state, giving it a language acquisition device that we can then study and thereby come to know more about our own linguistic development. So, thank you.